Hello everyone, today we're finally going to start our second chapter, motion. I don't know how many videos this is going to take, but we're going to start today. So the first thing that we're going to discuss is speed. Okay, so speed is the distance traveled per unit time. The formula for speed is distance divided by time. Now speed is a scalar quantity, and that is because it is calculated using distance, which itself is a scalar quantity. Moving on, we have velocity. Velocity is the change of displacement per unit time. So the only difference between speed and velocity is the distance and displacement. Speed uses distance while velocity uses displacement, and we'll talk about this difference in a while. So let's continue. The formula for velocity is displacement over time. Now in this case, displacement is denoted using s, so don't get confused. Okay, this s represents displacement. Now velocity is a vector quantity, which means that it has a magnitude and a direction. So let's look at the difference between speed and velocity. Okay, so the first example we've got a car, and the car is moving in the north direction. Okay, so the speed is 20 meters per second, while the velocity is also 20 meters per second. In the next round, the car moves back towards south. Now the speed will remain 10, it's positive because it is scalar, while velocity is minus 10. That is because it is going in the opposite direction of its original velocity, which is north. So the magnitude became negative. Okay, so another example we have is that we've got a track, this circular track denoted by this black line, and we've got a car, this red car on this track. Now the car is moving with a constant speed of 10 meters per second around this track. Okay, so it has a constant speed of 10 meters per second. It has a uniform speed, but this car does not have a constant velocity. This is because the velocity of the car is changing constantly. Like in this example, the car is moving in this direction, but when the car will reach here, its direction is going to be this way. If it comes here, its direction is going to be this way. So it's constantly changing direction, and as the direction changes, so does the velocity, because the direction is not constant. So this whole difference is only because of distance being used in speed and displacement being used in velocity. As you know, the distance does not have a direction while displacement does, and this displacement direction is added on to velocity, which gives velocity its own direction, and that makes velocity a vector quantity. So always remember this difference. This is a very key difference. Okay, so the next thing we're going to talk about is average speed. This is a very real world scenario. So as you know that if we travel from one place to another place, our car is not always in constant speed. It's always braking, or it's always speeding up, or there's going to be a rough patch somewhere, so we're going to slow down, and if it's clear, we're going to make a car go fast. So for this kind of journey, we need an average speed that can be used to represent the average speed of the whole journey. So what we do is that we divide the total distance by the total time taken for the journey to find the average speed. So in this example, we've got the distance A to B as 500 meters, and it took the car 100 seconds from A to B. Now as we can see, the car is going 20 meters per second in the first patch, then it's going to go 10 meters per second, and then 5. So it's very hard to calculate the average speed in this scenario. So we're going to use the distance and time. We take the 500 meter distance and we divide it by the time, which is 100 seconds, and we get the average speed of 5 meters per second. Okay, so the next concept that we're going to talk about is acceleration. Acceleration is the rate of change of velocity. So now what this means is, for example, you're going in a car and it has the velocity 10 meters per second, and you see that the road is clear, so you put your foot on the throttle and the car starts to accelerate. Its velocity starts to increase, and then it increases to 50 meters per second. So you see that the velocity has changed. It has changed from 10 to 50. This is the change in velocity, and to calculate acceleration, we we divide this change in velocity by time. So whatever time it took from going 10 to 50, we're going to divide it by the change. Now what's the change in velocity? It's 40 meters per second in this scenario. So let's continue. In the next, we've got the formula for acceleration, which is change in velocity. This triangle is called delta V, and this denotes that the change in velocity basically, and it is divided by time, which is in seconds. Acceleration is also a vector quantity because we use velocity to calculate it. It has a magnitude and a direction, and acceleration can be positive and negative as it is vector. Okay, so we've got an example here. We've got a cart at rest. It is at 0 meters per second in the start at point A. Then its velocity starts to increase, and it increases to 15 meters per second in a time of 3 seconds. So let's look at the steps. The car was at rest, which means that its velocity was 0. After 3 seconds, it was at 15 meters per second, which means that there was a difference in velocity of 15 meters per second. The change in velocity was 15 minus 0. And now we're going to calculate acceleration. As we know, the difference in velocity was 15, so we put it in the numerator and we divide it by the time taken, which was 3 seconds. So 15 divided by 3 is equals to 5 meters per second squared. Now this meters per second squared is the unit for acceleration. So let's try to make sense of this. So as we know that acceleration is delta V over t. Now if we look at it closely, the units for velocity are meters per second, and then the units for time are second. So we can write this as meters per second divided by seconds, and if we just do a little bit of maths, we can see that this comes down to meters per second multiplied by 1 over second, and acceleration is equals to meters per second squared. So the unit for acceleration is meters per second squared. Okay, so let's talk a bit more about acceleration. So you see there are two types of accelerations. The first one is uniform acceleration, and the second is non-uniform acceleration. Okay, so let's talk a bit more about uniform acceleration. So what uniform acceleration means is that the acceleration is constant, that the velocity changes at a constant rate. So let's read. Velocity increases by 10 meters per second each second according to this graph. So you see at point 0 the velocity was 0. At this point our velocity is 10 and the time passed is 1 second. After 2 seconds our velocity has increased to 20, and after 3 seconds it has increased to 30. Now if we apply a little bit of logic, we can see that each second the velocity is increasing by 10 meters per second. With this we can infer that the acceleration is constant, the velocity increases uniformly, thus the acceleration is uniform. This helps us form a straight line graph of velocity against time. Now if we connect all these points, we can see that this is a straight line. Okay, so let's come to non-uniform acceleration now. Acceleration is not constant, it changes continuously. So we've got an example here. We've got this vacuum chamber, which is denoted by the square in black. So what vacuum means is that all of the air has been sucked out and it is just empty space inside. We've put an object inside the vacuum chamber, and if we let it go, the object is going to fall with an acceleration of 10 meters per second square constantly. Okay, as it is a vacuum, there is no air resistance, thus the acceleration remains constant. Now what if there was no vacuum? What if there was air around? So in that case the air resistance is a force which is going to act upon the ball. Okay, it is a force which increases as the velocity increases. So for example, if a ball is traveling downwards with a speed of 10 meters per second, the air resistance is, let's say, going to be 5 newtons. But if the same ball is traveling down with a speed of 50 meters per second, the acceleration is going to be more than 5 newtons. It's going to increase, so it's going to be like 50 newtons. We don't know for sure, but the point I'm trying to make is that as the velocity of the object increases, the A resistance also increases against it. So as the object, if we let this ball go, this ball will start accelerating downwards, its velocity will start to increase, and as its velocity is going to increase, the A resistance acting against it is also going to increase. Now when this A resistance increases, it's going to act against gravity. Like this green arrow, it shows that the gravity is acting downwards while A resistance will act opposite to it. So overall the force because of gravity is going to start decreasing, and because of that the acceleration on the ball is also going to start decreasing. So due to this, the acceleration will change continuously, it will decrease. Thus this is an example of non-uniform acceleration. So here we've got a graph to help you explain. Now if we look at it at the start, when the ball was just dropped, its acceleration was maximum at 10 meters per second square or 9.8 meters per second square. But as the ball gained velocity, the resistance acting against it increased and the acceleration started to decrease. Now if we look at the velocity time graph for this, we can see that in the start the acceleration is maximum at 10 meters per second squared. So that is why, if I zoom in, that is why the velocity increase in the start is a bit more steep. Okay, so the velocity increases by a large amount in the start, but as the acceleration starts decreasing, the change in velocity will start to decrease, because as the acceleration will decrease, the velocity will still increase, but it's going to be increasing in a smaller amount. So like for example, if previously in 1 second the velocity of the ball increased by 30 meters per second, so let's take the acceleration 10 meters per second each second in 1 second. After the acceleration has decreased, the velocity of the ball is going to, let's say, increase by 2 meters per second each second. That is why the line starts getting flatter around here, because the change in velocity is less. Okay, and when the A resistance is big enough to completely cut off gravity, the acceleration will become 0 meters per second square, and we'll see that the line representing velocity will just flat, because as the acceleration is 0, the velocity is not changing at all. So the velocity is going to constantly stay at, in this case, 30 meters per second. Okay, so let's talk about the concept of deceleration. So deceleration is same as acceleration, except it is in the opposite direction. Now we know that acceleration is a vector quantity, thus it has a direction. So if the direction becomes opposite, acceleration will also become opposite. This phenomena is called deceleration. I've got an example, so let's see. We've got this cart here which is accelerating with an acceleration of 10 meters per second squared towards east. Okay, in the second example here, we've got the same cart which is going into the opposite direction, accelerating with an acceleration of minus 10 meters per second square. This is because in the first scenario the cart was accelerating towards east. In the second scenario it's going into the opposite direction, which is west. So the magnitude has become negative. We can call this minus 10 meters per second square of acceleration, or just simply remove the negative sign and call it deceleration. So 10 meters per second square deceleration. Okay, so this is it for the first lesson. I'll be uploading another video, maybe 2, to cover the whole of motion, and the next videos are going to be very important because they talk about graphs. I hope you understood, and if you've got any questions, you can drop them down in the comment section below and I'll try my best to answer them. Thank you.